Welcome to Lecture 13.6, Integration by Parts. This is the final lecture in this course, Math 1325, Calculus for Business and Social Science. So congratulations for making it this far. Integration by parts is a technique that we're going to use when we have a formula that involves integrating a product. And so we're going to look at the differential of a product. Remember the product rule? That when we take the derivative of a product, in this case two functions u and v, that the derivative of a product is the first function times the derivative of the second plus the second function times the derivative of the first. So if we slightly rearrange this equation by subtracting v du from both sides, as we get u dv on one side and then we get d uv minus v du on the other. So we get the equation of u times the derivative of v equals the derivative of the product of uv minus v times the derivative of u. Now if I integrate both sides, remember I can integrate the right side by taking the integral of each piece of the subtraction of the difference. And so what I get here, and remember that an integral is an antiderivative, so the integral of a derivative is simply the argument. So I get this function that if I have an integral that I can identify through substitution as u dv, then I can integrate it by parts by finding each of the parts, u, v, du, and dv, and it equals this formula, uv minus the integral of v du. And this is the formula you need to know to do integration by parts. So let's look at our first example. Here we have the product of x times e to the x. So our first step is simply to find a substitution for u and dv. And so what we do is we assign one of these functions a value of u, and everything else becomes dv, or the derivative of v. So in this case, we're going to set x equal to u, or u equal to x, and dv then becomes everything else, which is e to the x dx. Now, when we have these two parts, we still need to find the derivative of u, so we take the derivative of u, and so du is simply 1 dx, because the derivative of x is 1. And we assign dv, but we need to find the value of v, so we take the integral of dv, because the integral of a derivative is that original function. The integral of e to the x, as we see here, is simply e to the x. So now that we have all parts, we have u, v, u, and dv, we can set up the right side of the integration by parts equation. So we get u, which is x, v, which is e to the x, minus the integral of v, e to the x, du, which is simply dx. So the integral of e to the x, we already know, is e to the x, so this simplifies into x, e to the x, minus e to the x plus c. Notice that you might have looked at this and say, well, didn't we do ones like this before? We did do similar problems here where the exponent was a function. But here notice that if we did a substitution and made x equal to u, for substitution, du would equal just 1. And we still have this factor of x. We can't add or subtract a factor of a variable, only constants, remember. So we don't have a method for solving this until now, which is the integration by parts. Now there's another method that we can use, and it works really well typically with power functions, and it's called the table method. The first step in that is also to define u and dv, which we already did previously. Notice this is the exact same problem. We're just going to use a different method to solve it. The table method says to create a two-column table. The first column is labeled D, and that's where we're going to put the u value in the first row. The second column is labeled I, and that's where we're going to put dv into that first row as well. D stands for derivative, I stands for integrate. Okay, so once we have placed the the u and the dv in the first row, what we're going to do is we're going to differentiate the first column until we get to 0. I'm sorry this is all filled in, but notice that the derivative of x is 1. The derivative of 1 is 0. And that's going to tell us how big our table is. So we keep taking the derivative until we get to 0. On the right column, we're going to integrate those same number of rows. So although these all look the same, remember that the integral of e to the x is e to the x. And then we're taking the integral of this line, second row, to find the third, but the integral of e to the x is e to the x. So don't be confused by this example, this first example. We'll see more. What you're going to do is take the integral of each row to find the next row for the second column. Now this is kind of curious. What's going to happen is we are going to add and subtract the product of alternative diagonals. So here we have a diagonal, and the product is x e to the x. Now, in doing these tables, I would no longer write the dx. Let's just write the function. Don't write what you're differentiating with regards to, because dx is not a variable. It's more of an indicator for what we're differentiating or integrating with respond to. And again, we're going to add and subtract alternating diagonals. So the first diagonal is always positive, or we start with a positive. The terms could make it a negative. So the product of the first diagonal is x e to the x. We're going to subtract, as you can see here, the second diagonal with the product of the second diagonal, which is 1 times e to the x. So we get x e to the x minus e to the x, and we add our constant. If we had another diagonal, we would add it, and then another, we'd subtract it, as you can see here. So we're going to add and subtract. So we get diagonal 1 minus diagonal 2 plus diagonal 3 minus diagonal 4, etc., etc. We start at positive, and then subtract, add, subtract, add, subtract. Okay? So this is really helpful when we have more involved derivatives, and then when the table gets longer, it's a little bit simpler to do the table method. So let's look at another problem. Actually, before we get there, let's figure out how we pick parts. Notice that in that first problem we did, if we did the opposite, if we set u equal to e to the x and dv equals x to the x dx, we would not have got the same answer. In fact, we would not have been very successful in trying to solve this. Okay, so it's very important to pick your u specifically. So what we're going to do is we're going to give you a little an acronym to figure out how to pick u. So first you see is, are there any logarithms? If there are, that's your u. If not, are there any polynomials or powers? This is any variable or any variable with a power on it, like x squared, x to the third, etc. If there aren't any polynomials or logarithms, then we look for radicals. If there are any radicals, that's our u. If there aren't any radicals, then we go to the last, which is the exponential, and this would be e to the x, etc. And there's an easy way to remember this. First of all, remember that after you pick your u, dv is everything left. You don't have to worry about finding du and the factoring. dv just simply becomes what is left. Okay? So there's an easy acronym to remember this, and here you see a nice little lazy dog picture. Lazy, logarithm, people, polynomial, rarely, radical, exponential, exceed. Lazy people rarely exceed. This is a good little acronym to help you remember the order in which you pick the u, remembering dv is everything left. Okay, time for another problem. So our first thing is to pick the u and the dv. Do we have any logarithms? Why, yes we do. We have the natural log of x. So our dv is everything left, which is x dx. We find du by simply taking the derivative, and remember the derivative of natural log of x is 1 over x. And we find v by taking the integral of x dx. The integral of x dx is x squared over 2. Now we have all our parts to do the formula. So we get u v minus the integral of v du. Notice inside the integral we have a little bit of a confusing function, or a function that could be simplified. So we're going to simplify it first. And we're also going to rearrange the order of uv so that it's kind of more in line with math notation. So we get x squared over 2 times the natural log of x minus the integral of x over 2. Well, this is the same thing as 1/2 times the integral of x. Again, a pretty simple problem to solve. Okay? So we get x squared over 2 times natural log of x minus x squared over 4 plus c. Now the table method works a little bit differently for logs. We still plug in the u under the derivative. We still plug in dv under the integral, our I. And now we take the derivative of the natural log of x, which of course is 1 over x. All right? When we're doing a table with logarithms, as soon as we get rid of all logarithms in u, we stop. So this table is already done. We only have 2 rows. When we take the integral of x dx, we get x squared over 2. Now the way it works differently here is that we also use the bottom row in a logarithm table. Okay, so we have the integrals plus and minus like we do for the diagonals, but the bottom row is actually an integral. So here we have our first term is x squared over 2 log of x minus the integral of the bottom row, which is 1 over x times x squared over 2 dx. But again, this is an integral, so if we simplify this, we get the integral of x over 2, which we already saw above. So although we can use the table for logarithms, it's a little more confusing, and notice what it does is it just pushes us back into using the equation, because the bottom row becomes another integral of v du at the very end. Okay, notice we get the same answer, but we had to do the same thing. So the table doesn't really necessarily help us a lot with logarithms, and we have to remember that it works a little bit differently. Let's try another one. Here we get the natural log of x squared. Oops. So again, we have a log, which is the u. Remember, dv is everything left. Now be careful here. X squared is not a factor, it's the argument. We're taking the log of x squared. So this whole thing is one term. The only thing left is dx, and that's okay, because dv equals dx, we can still integrate that. So if we're looking for du, we take the derivative of the log of x squared. This is a chain rule. The chain rule says that we take the derivative of the outer function, which is the natural log, which is 1 over x squared, times the derivative of the inner function. The inner function is the argument, x squared. The derivative of x squared is 2x. So we get 2x over x squared, or 2 over x, when we simplify. The integral of dx, notice this is the integral of 1 dx, and the integral of 1 is simply x. Alright, so now we have our parts. We plug them in, u, v minus v du. We simplify the argument, and we have our answer. X, natural log of x squared, minus 2x plus c. If we plug this into the table, our u, then we take the derivative, we get 2 over x. dx, we take the integral, we get x dx. We have our first term, minus the bottom row, which is an integral, and we're back to where we started up here, and we get the same answer. Whoops, sorry, I went a little fast. So the table does work, it's just a different table, etc., and I don't know that it's much easier in this problem. Let's look at a problem where the table really does help us out. So again, here we go. Do we have any logarithms? No. Do we have any polynomials or powers? These are variables with exponents or just variables? Yes, we have x squared. That is our u. So our dv is everything left, e to the 2x dx. Once we have our u and dv, we find our du by taking the derivative, which will give you 2x. We find our v by taking the integral, and this will be 1/2 e to the 2x. I'm not going to walk through this. You should be able to do the substitution and integrate this function, no problem. Once I have all the parts, I now use my substitution, u, v minus v du, and Houston, we have a problem. Notice what we have in here is another product, and we cannot do the substitution, because if we make 2x be u, the derivative of that is 2, and so we also have this extra x factor. So we actually have to do substitution by parts, or integration by parts, a second time. So now we have to go through this all again. Do we have any logarithms? No. Do we have any polynomials or powers? Yes, that's our x. So u equals x, dv is everything else, e to the 2x, du, the derivative of x is 1, the integral of e to the 2x is 1/2 e to the 2x, and so now we have all our parts for this piece. Notice we're subtracting them, so we have to put it all in parentheses, u, v minus the integral of v du. Now we're at a place where we can actually integrate the last piece, and we get this function here. 1/2 x squared e to the 2x minus 1/2 x e to the 2x plus 1/4 e to the 2x. You might recognize that you have e to the 2x in all of these, so you could factor it out. Also, 1/4 goes into all of the coefficients. You could factor it out, but this last step is really not necessary. Now, one of the neat things is this is the exact same problem. So I'm getting the substitution up there that we did before. And we saw that when we plugged it in the first time, we actually had to do integration by parts twice. And it's problems like this where the table really can help and just get to our answer finally. So once we're up here with u and dv, right, we've got them there. Remember, we integrate u until we get to 0. The integral of x squared is 2x. The derivative of x squared is 2x. Remember, we're differentiating the first column. The derivative of 2x is 2. The derivative of 2 is 0. Okay? So here, then I'm going to integrate on this side. And it's nice that we finally see that there are different values. The integral of 2x is 1/2 e to the 2x, or e to the 2x over 2. And again, you do that by substitution. U equals 2x, so du equals 2. So we have to have a factor of 1/2 on the outside. Okay? So we keep having a factor of 1/2, so the derivative of this function is e to the 2x over 4, because we're talking using it by 1/2. And the derivative of this function is e to the 2x over 8. You can take these integrals, and indeed you should, just so you get the practice. Okay. Remember then, we add and subtract alternative diagonals to get our answer. So once we have this done, we have our answer. X squared e to the 2x over 2. Notice here we have 2x e to the 2x over 4, so the 2 and the 4 simplify. Oops. So the 2 and the 4 simplify, my bad. And then here we have 2e to the 2x over 8, and these simplify to e to the 2x over 4 plus c, which is the same answer. So when we have these involved power functions that maybe have a square or better, the table is definitely the way to go. All right, so that finishes up our lecture for the entire course. You've made it all this way. Congratulations. Good luck on your last test and the final exam.